calling these thought experiments and having you guys guess or kind of predict what's going to happen is a good way of actually exposing you to a lot of different phenomena that we're going to cover, while at the same time, testing your guys' instincts and how well they naturally incline with the topic that we're going to be going over today. So let's begin going over what is called a charged model. Oh, wait. Yeah. So developing a charged model. Now, let's begin by going over a few scenarios, which I'm sure most of you guys, if not all of you guys, have experience with. So let's consider the following. What happens when you touch a doorknob after skidding across the carpet? Yes, get shocked. You've done this before. So you touch a doorknob after skidding across the carpet. What results is a shock. What about if you rub your hair, if you have any, with a balloon? What happens? Yeah, it's able to stand up or it's attracted to the balloon, right? So hair stands up. Or is attracted to the balloon. Now this balloon, you'll notice, can also pick up dust particles and things like this. Balloon. Right, this balloon, the one that you rub your hair with, balloon can pick up dust. So what do these have in common? It is that rubbing objects together leads to sparks or forces. So here, the shock, if you do it with the lights out, you're going to see that it actually lights up for a brief moment. Also, here, the hair is able to stand up, meaning it's able to fight gravity. It's attracted to the balloon, meaning obviously there's an attractive force going on. And the balloon can also pick up dust. Once again, there's forces. So rubbing objects together leads to these weird behaviors. And of course, we have the question, why? Why does that happen? And of course, we want to ask this question in a more precise fashion. We want to know, what are the forces? What are the forces at play? And this idea of sparks and this weird attractive force that's happening, both of them share the same phenomenon of electricity. And so the answer We're going to call it electric charge. Electric charge. Now these are a few real-world observations, but we care more deeply about having a precise understanding of what these are, how do they behave, and so that how can we take advantage of them. To do that, we need to develop a charge model. Now this is where we're going to go into our laboratory of your minds, or what I call, we're going to do thought experiments. So these are the tools that we're going to be utilizing for our thought experiments. The first one, we're going to have different rods. We're going to have plastic, and glass rods. Secondly, we're also going to have different types of cloth. We're going to have wool and silk. Third, we're going to have a metal rod and metal spheres on wooden stand. Now we're going to be doing 3 sets of thought experiments. We're going to do roughly like 12 total, but we're going to group them into 3 different sets of thought experiments. For these, they're going to be thought experiments number 1 and 2. For this one, we're going to be utilizing thought experiment number 3. So let's begin thought experiment number 1. Now, no experiment is meaningful without a control, so let's identify our control experiment. The control experiment is we're not going to rub any objects together. And in our control, what we're going to be doing is we are going to be hanging a rod from the ceiling, and we are going to be bringing to it, within close proximity, a second rod. Neither one of these rods were rubbed. So what do you guys think will happen between these 2 rods? The options are repel, or attract, repel, or no interaction. Who says they will attract? Raise your hand. Who says it will repel? Raise your hand. What about no interaction? Raise your hand. All right, yeah, we're good. In this case, there is going to be no interaction. No interaction. So our base case is nothing happens. So as soon as something happens between the 2 rods, we know that something happened. So let's begin with experiment number 1. We are going to rub wool with rub plastic with wool. Rub the plastic with the wool. And we're going to do that with both rods. So originally the rod was just hanging vertically like this. And we are going to rub the plastic rod with wool. to both this rod and the one that we are going to be bringing into proximity. So let's say for both. Now let's gauge your guys' intuition. This rod, do you think it will be attracted to this rod? Do you think it will be repelled by this rod? Or there's going to be no interaction? Who says that it's going to be attracted? Raise your hand. Confidently raise your hand. We're gonna raise. Who says they will repel? Raise your hand. Who says nothing happens? Raise your hand. Okay, the answer is the rods are going to repel. Rods repel. Oh, one thing, the rods are never ever made in contact. And so no contact is being made. You're just bringing one rod in close proximity to the other rod. Let's do the second experiment. Instead of plastic with wool, we're going to be replacing both rods with glass. Rub glass with silk. And this is for both. So our scenario doesn't change. In the control, the rod was originally just hanging vertically. This time we bring a glass rod rubbed with silk, and we are bringing it into close proximity to another glass rod rubbed with silk. And the options are the same. Is it going to attract, repel, or no interactions? Let's see a show of hands. Who says they will attract? Raise your hand. Who says they will repel? Raise your hand. Who says nothing will happen? Raise your hand. Well, nobody got this right. They will repel. Rods repel. Yeah, isn't that interesting? Now, instead of having plastic and plastic and glass with glass, what's the next combination you could do? You could swap. See the plastic with the glass. So that's going to be experiment number 3. Rod 1 is going to be plastic plus wool. The plus meaning that's what the rubbing combination. Rod number 2 is the glass plus the silk. Okay. Now really, it doesn't matter which one is which. So it's just one of them is plastic, that's been rubbed with wool. The other one is glass, that's been rubbed with silk. Okay, who says the rods will attract? Raise your hand. Who says they will repel? Raise your hand. Who says no interaction? Raise your hand. And this time, the rods will attract. Rods attract. Oh, I forgot to draw this one. This one repels. Now, experiment number 4. We see this behavior happening, but it's only happening when it's rubbed. So we want to know, can we control the strength of the interaction with rubbing? So how vigorously you rub, do you think that will impact the strength of the interaction? Who says stronger rubbing leads to stronger interaction? If it's meant to repel, it will have a stronger repulsion. So in experiments 1 and 2. In experiment 3, they're attracting, so it'll lead to a stronger attraction. Who thinks more vigorous rubbing will lead to stronger interaction? Raise your hand. Okay, yeah, that one is true. So let's just say stronger rubbing led to a stronger interaction. Now, one of the things that we discussed was that these are not touching. These are not touching. None of these are touching. Which leads, obviously, to ask, well, is it distance dependent? So that's another thing that we want to assess in experiment number 4. Who thinks it gets weaker with distance? Meaning the further you are, the weaker it gets. The further you are, the weaker it gets. And that one is also true. So there is a distance dependency. Meaning weaker with distance. So those are our thought experiments so far. This constitutes our first set. But before we move on to the second step, let's analyze the information that we can gather from these thought experiments. So let's do a little bit of analysis. Now, in the control, there were no interactions, meaning there were no forces that were present. Whereas in experiments, well, the other experiments 1, 2, 3, and 4. Well, let's just say 1, 2, 3. There were interactions. There were forces. Comparing our experiments to the control, we can say that there is a categorically different behavior that's occurring. So we need a way to distinguish these no forces from the presence of forces, and this is where we introduce the term neutral for when there are no forces. So in the control, we would say the objects are neutral. To distinguish the rods from something that can actually have interactions. Whereas if there are forces, instead of saying they're not neutral, we can apply a positive term. We would say objects are charged. Objects are charged. And we know exactly what led to the charging because we rubbed the plastic with the wool or the glass with the silk. So here, rubbing led to charges. This is the process called charging. This is called charging. Also, one of the details that I mentioned was the rods were never ever made to contact. Meaning that these are long range, no non-contact forces. So no contact, meaning that this is a long range force. Long range force. Now in the fourth experiment, or sorry, in experiments 1, 2, and 3, we just cared about, is it attracting, is it repelling, or is it nothing? But we didn't care about the strength which the attraction or the repelling was occurring. In experiment 4, that's where we tried to explore what's actually leading, or what are some things that actually can change or alter the strength of the attraction and the repulsion. So in experiment 4, we found that the force had at least 2 variables. The first one was distance. How far apart are the 2 objects located? The other variable was how much the rods were rubbed. So the force is a function of distance as well as the amount of rubbing, or the strength of rubbing. Now, if you recall back from Physics 1, we had 2 broad categories of forces: contact versus long range. The interactions that we're seeing here is long range. What is the other long range force that we've encountered thus far? Gravity. Gravity does not require contact. So, aside from gravity, this is the first long range force. However, these observations led to something that's very distinct from gravity. Can you guys identify what that is? So, there's a lot of things that the interactions that we've observed here share with gravity. However, there is something very unique and distinct from gravity that we've seen so far. Yeah.
Is it that it can hold an object and push the object in pretty much any direction? It's not just down.
Well, what is down? Because the moon, Earth, and the moon, the Earth is, if the, if the Earth is up here and the moon's out here, it's pulling it up, right? So not quite. Although I thought you had it. So it does kind of have something to do with direction. Gravity can only attract. What did we see here? There's a push force, a repelling force. So, but this repels. And this leads us with a few different questions. So for sure, our first set of thought experiments gave us a lot of valuable information. We can already distinguish neutral versus charged objects. We can see that they can push and pull, or attract and repel. But even though these gave us more information, we also got a few different questions. One of the questions being, why attracting and repelling. How is that even possible? How does it attract and repel? So we have at least one question. There's a few more, and that's what will lead us to thought experiment number 2. So back to the lab we go. Now, so far in our first set of thought experiments, all of the objects or all the rods were charged in some way, shape, or form aside from our control. So there's a still question remains, well, how do charged objects interact with neutral objects? So let's assess that. So this is going to be experiment 5. So here, this is, okay, instead of constantly saying plastic plus wool, we'll just say plastic rod, okay. Meaning it's charged, it's a plastic rod that's been charged by rubbing wool, okay, or plastically charged rod. Now let's say we bring it in close proximity with small pieces of paper on the ground. And these pieces of paper, let's say, are neutral. What do you guys observe? Would it attract? Would it repel? Or no interaction? Who says they will attract? Raise your hand. Who says it will repel? The piece of paper will be repelled by the rod. Raise your hand. Who says, well, the papers are neutral, so no interaction? Who says no interaction? Raise your hand. Okay, it's like an even split. 30, 30, 30. The rod will attract the pieces of paper. So rods will attract neutral paper. Well, that was a plastically charged rod. Let's repeat this experiment with glass, glassically charged rod. And we're going to bring it over those same neutral pieces of paper. What do you guys think you will observe? Do you think the pieces of paper will be attracted, repelled, or no interaction with the rod? Who says the rod will attract the pieces of paper? Raise your hand. Who says they will repel the neutral pieces of paper? Raise your hand. Who says no interaction? Raise your hand. Okay, this time it was like a 25, 25, 25, 25 with 25 not responding. Okay. The rod will attract the neutral pieces of paper. Now, isn't that peculiar? This time, the plastic and the glass do the same thing. So maybe it has to do with the paper, so you go back and you do the rods experiment. So this time you have you hang a charged rod. And within close proximity, you bring a neutral rod. Oh, this was experiment 7. Now, attract, repel, or no interaction. In this scenario, who says they attract? Raise your hand. You have charged versus neutral. Who says they will attract? Raise your hand. Who says they will repel? Raise your hand. Who says no interaction? Raise your hand. Well, just like in experiment 5 and 6, where the plastic attracted the neutral and the glass attracted the neutral, the charged is going to be attracted by the neutral. So charged rod attracted to neutral. Now, it seems like we yeah, question.
Sorry, I was just gonna say, so if that attracts it, then why did the experiment to repel it if it's the same setup?
Experiment 2 is not the same setup.
But
Both
it's-
are plastic rubbed with wool.
Oh.
Neither are neutral in experiment. Oh,
Sorry.
neither are neutral. None of these are neutral objects. All of them are charged some way, shape, or form. In experiment 1, they're both plastic. In experiment 2, they're both glass. Experiment 3, one is plastic, one is glass.
Okay, I misread your.
So it seems like we've exhausted pretty much, all the different possibilities of charged versus neutral. Although that might be kind of true, there's an important object that we want to see an interaction with. Here, to charge these objects, we're rubbing the plastic with the wool. We're rubbing, and these for glass rods, we're rubbing the glass with the silk. How do you think the plastic and the wool will interact after you rub that? Right, isn't that an interesting question? Let's do that as experiment number 8. So you have a rod, and within close proximity, so let's say this is plastic and this is the wool. So a wool with which, how do I work this? Wool which was used to rub plastic in close proximity with said plastic. Once again, 3 options: attract, repel, or no interaction. Who says they will attract? Raise your hand. Who says they will repel? Raise your hand. No interaction. Raise your hand. In this case, it will attract. And it's going to be the same scenario with the glass and the silk. Same with a glass silk combination. question.
Would that work if we're rubbing it wool with silk?
No, so, okay. It might be worth. So if you rub plastic with silk, you will get a very small interaction. If you rub glass with wool, you'll get very small interaction. And that's because hopefully everyone's taken some level of chemistry. It has to do with the electronegativity of the object. If they have similar electronegativities, then rubbing it's not really going to do anything. You need to have a significantly different electronegativity, then will you get this charging effect that we have. And so glass and silk doesn't work. Or sorry, glass and wool does not work. Plastic and silk does not work. It has to be the proper combinations. Yeah, but I gave you that because we're not going to do a thought experiment. Although, I guess the next one's kind of like it. So here we've identified plastic and glass. They attract each other. They attract each other. They also repel. If glass repels glass, plastic repels plastic. But experiment 7, we observed charged rod. So this is both plastic and glass. Both plastic and glass are attracted to neutral. Now, of course, that leads us to ask the question, is there something that will repel both plastic and glass? Or if there's something that can attract both, maybe there is something that can repel both. So, you go back into the lab. And you hang two rods. One is plastic. I'll just draw like this. One is plastically charged. The other one is glassically charged. And you bring to it in proximity. So here, we'll just put it as a question mark. Is there any object that you can place within its proximity such that both rods will be repelled by the same object? So here, in experiment 9, we're just answering a very specific question. It's an exploratory experiment. So, any object that repels both glass and plastic who thinks there is, raise your hand. Who thinks there is not, raise your hand. Oh. Indeed, there is not. Even though a neutral object will attract both the plastic and the glass charge, there is no object, at least that's known to us at this current point in time, that will repel both plastic and the glass rod at the same time. And that concludes our second set of thought experiments. Now let's do a little bit of analysis. Do a little bit of analysis. Now, thought experiment number 1, just as a brief summary, we could say that we saw that charged objects exert forces on each other. I know there's, repelling and attracting, but this is just a summary statement. But let's do a little analysis on our second set of thought experiments. Experiments 5 and 6 demonstrated that not only do charged objects exert forces on each other, but they exert forces on neutral objects as well. Well, that also includes experiment 7. So experiments 5 through 7. So here, experiments 5 through 7 show charged and neutral attract and only attract. And with these, we can begin developing what is called the charge model. That is a set of hypotheses that seems to be consistent with the experimental observations we made thus far. Charge model number 1. First is to understand exactly how the objects are being charged. It was the act of rubbing. But what is rubbing? In a more physical sense, rubbing is simply the application of frictional force. So we would say frictional forces add charge. And of course, one of those experiments showed us the relationship. More vigorous rubbing leads to higher charging. Oh, by the way, the lab this Thursday, essentially you guys are going to be doing, kind of like these set of experiments. You'll actually be doing that in the lab on Thursday. So this wasn't just purely theoretical. You'll see some of those elements. And you'll definitely be doing this. So, yeah. A second hypothesis we can write is that there are only two kinds of charge. We saw that plastic and plastic, or plastic and glass, they attracted each other. Also, they repelled, their own kind. But we tried to exhaust all the different kinds of objects that we can bring into close proximity. None of them actually repelled each other. And so that eliminates the possibility of a third kind of charge, at least that we know of thus far. So we can say that there are only two kinds of charges. Right now, we are going to call them plastic and glass charges. Our third hypothesis goes over exactly how these charges interact with each other. That is, like charges repel. We saw the plastic repelling the plastic. We saw the glass repelling the glass. And the old adage, opposites attract. Like charges repel and opposites attract. Fourth hypothesis, we already made note of this, but for the sake of completion, let's do it again. These are long-range forces. Because no contact was necessary, and we saw that there was distance dependency. Distance dependent. 5. Before the rods were rubbed, they began as neutral. But it's only when it was rubbed, or plastic was rubbed with wool, did it become, plastically charged. And we saw that the plastic with the wool with which it was rubbed, they attracted each other, meaning they had opposite charges. Right? They had opposite charges. So, it seems like the wool stole some charge from the plastic, some opposite charge. So if the wool were to give it back, the plastic would become neutral once more. Meaning, we can conclude the following. Neutral objects have equal amounts of plastic and glass charge. Neutral objects have equal plastic and glass charge. Right, this is actually a lot of information that we gathered from just a simple set of thought experiments. Now, before we proceed, there are a few important things that we need to discuss. The charge model is derived from observations. One of the implications of this is the following. These hypotheses have not been proved. So hypotheses are not proven. Science can never prove anything, or can never prove a hypothesis. Science can only demonstrate that whatever your hypothesis is has yet to be falsified. For all we know, let's say for this one example, there's only two kinds of charge. Well, that we know of. We might go onto a different planet, and we might do that very soon because Elon Musk really wants to leave Earth, right? Yeah, maybe in a different planet, he finds a material and it actually can repel both plastic and glass, at which point we would have to throw all of this away and have to rediscuss, all of physics. So, just because it's from observations, meaning all of science is, no hypothesis can ever be proven. Meaning, a different set of hypotheses can be equally valid. And you could come up with your own set of hypotheses as long as they don't contradict any of the observations. We would have to say that they are equally true, at least with the observations that we've had up to this point. Well, that's the nature of science. It can never prove any hypothesis correct. So those are the first two sets of thought experiments. However, we still have a few lingering questions. First, so we have still unanswered. One. Why do neutral attract both charges? That seems kind of counterintuitive. You would kind of expect opposite behavior, right? Opposite charges. Another question that we still have is, I told you guys in our set of tools that we're going to be using metal rods and metal spheres. How do they kind of behave in this fashion, or in this kind of scenario? We care about the behavior of metals. Unfortunately, the first question we're going to come kind of in like either next week. Yeah, I don't know if we're going to be able to, actually we might get to it on Wednesday. So we're not going to answer this quite yet. We're going to move on to the behavior of metals. So that's what thought experiment number 3 is intended to tackle. Let's do thought experiment number 3. Thought experiment number 3. What number were we on? Experiment 10. Now in this scenario, we're going to bring about the metal sphere on the wooden stand. Let's say around this metal sphere, there were the tiny pieces of paper that were neutral in close proximity. Now, if the metal is neutral, nothing's going to happen. So, what we're going to do is we are going to bring near it a charged, let's call it charged plastic. So it's plastically charged, and this time we are going to make contact. We're going to touch it. So we charge a plastic rod and touch metal. Now the same scenario. Will the metal attract the pieces of paper? Will it repel the pieces of paper? Or will there be no meaningful interaction? Let's see a show of hands. So the metal was originally neutral, but then we touch a plastically charged rod. Who says the metal sphere can now pick up the pieces of paper? Who says they can attract? Raise your hand. Who says the metal sphere now will repel? Raise your hand. Who says no interaction? Raise your hand. Indeed, metal will attract pieces of paper. Meaning, or a little side note, just making a mental note, the metal seems to have acquired the plastic charge. So the metal seems to have acquired the plastic charge when the contact was made. Well, let's go a little bit further. Instead of a single metal sphere, let's say we have 2 metal spheres. And there's those neutral pieces of paper right around them. And let's say we bridge the two metal spheres with a plastic rod. It's not charged, it's a neutral plastic rod. And let's call this the sphere on the right, sphere A. Sphere on the left, we'll label that B. Into sphere A, we bring into contact a charged plastic. So charged plastic, and then we make contact. Of course, experiment 10 tells us we would expect sphere A to attract the pieces of paper. We want to know what's going to happen in this experiment with sphere B. Okay. With sphere B. So here, we connect two metal spheres with neutral plastic rod. Charge a different rod and touch sphere A. Now we want to know what's going to happen with sphere A and sphere B. What does this neutral plastic rod that connects them do? All right, sphere A. Who says it will attract the neutral pieces of paper? Raise your hand. Who says it will repel? No interaction? Yeah, it will attract the paper. What about sphere B? Will sphere B be able to attract the pieces of paper, or will they repel, or no interaction? Who says attract? Raise your hand. Who says repel? Raise your hand. Who says no interaction? Raise your hand. B will have no interaction. And that is very peculiar. So instead of a neutral plastic rod, let's utilize our metallic rod in its place. And that'll be experiment 12. So it's the same scenario, with the only difference being we are replacing the plastic rod with a metallic rod. So these are all metal. So it's the same as experiment 11, except replace plastic rod with metal rod. And again, we care about the behavior of the spheres and they have with the neutral pieces of paper on the ground. This is sphere A and this is sphere B. All right, let's do a show of hands. Who says sphere A, after this charged plastic makes contact with sphere A will attract the pieces of paper? Raise your hand. Who says they will attract? Repel? No interaction? And this, it will attract. Okay, what about sphere B? Will sphere B able to attract neutral? Raise your hand. Who says it will repel? No interaction? Yes, in this case, sphere B will be able to attract the pieces of paper. And that will conclude our thought experiment number 3. But let's do the analysis here. And by that, we are going to be adding to the charge model. So this is the charge model part 2. So hypothesis number 6. So if we compare experiments 11 to 12, what is the only difference between those two experiments? What is the only thing that changed?
The rod.
Yeah, the makeup of the rod itself, what kind of material it is. And there was a drastic difference between the rod being plastic versus it being metal. So comparing experiments 11 to 12 allows us to conclude that there are 2 types of materials. Two types of materials. And those 2 types, we give them the following terminology: conductors and insulators. Seven. Another hypothesis is that metal are charged not by rubbing, but by contact, by touch. So here we can say charge can be transferred via contact. Charge can be transferred via contact. So this is the brief introduction to this world of charge through a lot of these thought experiments. Like I mentioned, on Thursday you will have a in-lab experiment that kind of goes over the gist of thought experiment number 1. Of course, we're going to be using a slightly different scenario, but your goal is going to be pretty much what is encapsulated right there, but we'll get that. We'll get there when we get there. Let's do a simple example though. Let's say you have some object and you want to determine if it's plastically charged, neutral, or glassically charged. So to determine if an object has quote-unquote glass charge, it's a multiple choice question. Is it A, do you see if object attracts the plastically charged rod? B, see if object repels a glassically charged rod? C, you have to do both A and B? Or is it D, do either A or B? To determine if an object has glass charge, do you A, see if the object attracts a plastically charged rod? Or do you B, see if the object repels a glassically charged rod? C, do you have to do both? Or D, can you just do either one of them? Who says A? See if the object attracts a classically charged rod. Okay, who says B? See if the object repels classically charged rod. Okay, who says C? You have to do both A and B. Okay, who says D? Do either A or B. And the answer is only B. Why is it only B? Well, what kind of object, well, let's consider A. What kind of object or objects will attract a classically charged rod? It is a classically charged rod, but also there's another that will attract this, which is what?
Neutral.
A neutral rod. So A doesn't actually give you that information. A gives you a meaningless answer. Like, okay, yeah, if it attracts this, we still don't know if it has glass charge or if it's neutral. Only a classically charged rod will repel a classically charged rod, and so that's what you would have to do. So A provides you no information. It is a waste of time. It is only B. Alright, so that was the basic introduction. Now let's, for the remainder of the time, when does this class end, by the way? Is it 8 o'clock? Okay. For the remainder of time, let's actually begin developing the more comprehensive and technical version of the glass model, or the charge model, not the glass model, the charge model. So hopefully you guys get a different sense of what's occurring. So here, there are multiple kinds of charges. That's very important. Likewise, there's also multiple kinds of materials. That's also very important. And there's a lot of different features that are important, such as it is distance dependent and things like that. Okay, so you guys got a lot of exposure to different concepts and phenomena. Let's now actually get a little bit more precise and technical. So this is when the actual material will begin. So we're going to be talking about charge. First, it's important to understand that there's going to be two types of charges. We call them glass and plastic. However, you notice no one in this world ever called charge plastic and glass. Today we call them positive and negative. That is how these charges are actually differentiated. Does anybody know who coined this positive and negative charges? Any ideas? Any guesses? I'll give you a hint. He is not known to be a scientist, but more for his politics. Not Jefferson, very close, but the guy who got electrocuted by flying a kite.
Benjamin Franklin.
Benjamin Franklin. Yeah, this was coined by Ben Franklin. What number president was he? No, just kidding. He wasn't a president. Alright, but Benjamin Franklin called it positive and negative because he saw that it behaved like positive and negative numbers. So behaved like positive and negative numbers. However, this should lead you to a question. Plastic and glass, which one is positive and which one is negative? You're right, I don't know either. Ultimately, so the question, which is which? And the answer, there is no fundamental reason why the positive was called positive and the negative was called negative. Ultimately, it was convention. Ben Franklin said, ultimately the charges come from protons and electrons. Why is proton given positive charge and electron given negative charge? It's just because Ben Franklin did it that way. There's no fundamental reason why the proton has to have a positive charge and an electron has to have a negative charge. We could have easily been in a world where it was flipped. If the coin that Ben Franklin flipped happened to land on the other side, then we would be talking about protons that have negative charges and electrons which have positive charges. But we live in a world that's not the case, so yeah. Ultimately, yes, it's just convention. There's no fundamental reason why the positive had to have been positive. It was just the way that Ben Franklin named it. This idea of charge also helps us understand the atomic nature of things. How does the atom exist? So electricity. Or a more precise version of that question that actually gets to the main point at hand. Atoms have, electrons and protons all within itself. What do you know about like charges? They do what? They repel. Where are all the protons inside the atom? Huh?
Inside the nucleus?
Yeah, inside the nucleus. Where is the nucleus?
The
In the center. Why aren't the protons pushing each other's away? How can they be all clustered right next to each other when like charges repel? Right, this is a fundamental question that, that was the primary reason why nobody thought the nucleus existed until much, much later. And that is where, this kind of atomic view of electricity helps kind of rectify some of these ideas. These atoms are stabilized because of the opposites attract idea. So atoms are held together by attractive forces between protons which have a positive charge and electrons which have a negative charge. A shorthand notation I'm going to be using for protons and electrons. An electron is going to be E superscripted negative. A proton is going to be E superscripted positive. And why I call a proton E superscripted positive will be clear by this next statement. So let's properly define a charge. A charge is simply an inherent property of electrons and protons. You can kind of think of it like mass, except it's just something kind of different. Where does mass come from? Well, ultimately, these subatomic particles have them. It's just an inherent property with which they were made. Likewise, electrons and protons don't just have mass, but they have this other thing called a charge. And electrons have a charge. So charge, we give it the symbol Q. Q as a charge. The charge of an electron is negative E. What do you think the charge of a proton is? It's positive E. And that's why I called it proton E superscripted plus. So electrons and protons have equal but opposite charges, and they are identical. They are identical, except opposite. And the value of E is 1.6 times 10 to the negative 19th coulombs. You don't have to memorize that, although I think you should, just for simplicity. You don't have to memorize it because it's already in the handbook. This C is the unit of charge, and it is a coulomb. And it's the SI unit for charge. Yeah.
If you somehow took all the electrons out of an atom's shell, could you theoretically split the nucleus?
Yes. Except the electrons aren't what keeps the nucleus stable. I don't necessarily believe in all of this field, but this is where particle physics comes into play. And they say protons and neutrons are made up of these things called quarks, and they're the ones that are actually holding the nucleus together. Okay, you can read more into that. I don't necessarily believe everything that they come up with, because I think they don't really have good experimental observations. But that's where, who's heard of like the Large Hadron Collider? The things that they spend billions of dollars making in like Switzerland or something. Essentially, that's what they're trying to find out. What is the actual fundamental particle? Yeah. But I don't believe some of their stuff. Yeah.
What's the difference between that and a volt?
We'll get there.
Okay.
You're way jumping the gun.
Okay, sorry.
Yeah. But we will get there. That is important. But to answer your question in a general sense, Coulomb is fundamental. Volt is not. The volt is not a basic SI unit. Coulombs, along with a few other things, lead to a volt. So let's say a few statements about neutral objects. Everything is constituted of an atom, meaning everything has protons and electrons. So a neutral object is not the absence of protons or electrons, but the fact that there's equal amounts of them. So a neutral object has equal number of protons and neutrons. Not neutrons, electrons. Meaning, if the number of protons is greater than the number of electrons, then you have a positive charge. Or if the number of protons is less than the number of electrons, then you have a negatively charged object. From here, you should be able to see one additional observation. And that is, charges can only change by an increment of E. Charges can only change by increments of E because you can only have a whole electron or a whole proton, and every single time you add or subtract an electron, you're going up and down by a factor of E. So notice, amount of charge can only change by a factor of E. And I'll conclude with this interesting fact. So this idea here, this is how we were able to identify what this exact value of E is. Does anybody remember the guy's name or the experiment that led to the identification of the charge, the actual value of the charge, like this? Does anyone remember the guy or the experiment?
The gold foil.
Not the gold foil, that was the nucleus. Okay, those of you guys who have been in chemistry should know this. It was called the oil drop experiment. So within these oil drops, the guys noticed that, or just kind of assumed that because the charges are coming from something and it can only change by a discrete number of them, an integer multiple, he noticed that the oil drops, they were all a factor of E. Therefore, instead of identifying exactly how many electrons there were, he just noticed they're changing by factors of E. Therefore, this has to be the fundamental charge number. Does anyone remember the guy's name? The oil drop experiment?
Rube Goldberg.
Not Goldberg.
No.
Was a guy named Millikan. Another interesting factoid. Where I graduated from in Caltech, so it's like about an hour away. There's a 8-story library named after him. It's called the Millikan Library. And in honor of the oil drop experiment that he's famous for, during Halloween, there's a Halloween tradition where they freeze a pumpkin using liquid nitrogen, go up to the roof, and then drop the pumpkin off of the roof. Because when the pumpkin explodes, or when it hits the ground, they say it releases light very momentarily. I've never seen it. Right, but that's a tradition. Another interesting fact is he was known to have slaves, so now there's a huge push to have the library change its name. Yeah, so all of that's happening. All right, I'll see you guys Wednesday.